Hey team, welcome to the numbers game. I'm Coach T, and in this tutorial, we're going to be proving that our subset is indeed a subgroup. Now, before we get started, make sure to subscribe to the channel for notifications on more math tutorials. Now let's take a look at this example. So our example says, let G be a group. Show that H is a subgroup of G, and H is defined as x raised to 4 such that x is an element of G. So the first thing that we'll do is review the definition of a subgroup. Here's our definition. It says, let G in some operation be a group structure and let H be a subset of G. We say that H is a subgroup of G if and only if the following conditions are met. 1, we can verify the existence of an identity, or in other words, we can verify the identity of G is also in H. 2, H is closed under multiplication, or in other words, the product of A and B is in H for every A and B in H. And 3, H is closed under inverses. This means that for all of the A's in H, there exists an inverse of A in H such that A times the inverse of A equals the identity, which equals the inverse of A times A. If all of these conditions are met, H is a group in its own right, and H is a subgroup of G. So now that we've reviewed the definition of a subgroup, let's start to prove our example. Again, our example says that G is a group and we need to show that H is a subgroup of G, and H is defined as x raised to 4 such that x is an element of G. Here are the 3 conditions that H needs to satisfy in order to be a subgroup of G, and we'll just check them off as we move along in our proof. We'll start by letting A and B be elements of H. Then we'll have A equal x raised to 4 and B equal y raised to 4 for some x and y in G. So just so we're clear, x and y are the elements of G, and A and B are elements of H. The goal here is to show the relationship between these elements through multiplication, through inverses, and through a shared identity. All right, now moving on. If A equals x raised to 4 and B equals y raised to 4, the product A times B has a square root. And I'll go ahead and show why that is. We have x raised to 4 times y raised to 4. This expands to x, 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 and y, 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 y. This equals a factor of x times xy, xy, times a factor of y. And then we can flip the order of the x's and y's inside of the parentheses. So x times y, x, y, x. This gives us xy, 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 xy. So that's xy 4 times. So x times y raised to 4. So we've shown that x raised to 4 times y raised to 4 equals x times y raised to 4. Clearly, A times B has that square root we were talking about earlier, and so therefore H is closed under multiplication. So I'm going to check that off of our list, and let's move forward in this proof. For this next part, we'll define A as an element of H. Then we'll have A equal x raised to 4 for some element x in G. Now, since G is a group, by definition, the inverse of x does exist in the group G. Also note that x times the inverse of x equals an identity, and we need to find an inverse of A in H such that A times the inverse of A equals that same identity. So if we're able to do this, we're not only able to verify the existence of our identity, but we're also able to prove that H is closed under inverses. I'm going to quickly go back to our subgroup definition. And for H to be closed under inverses, we need to show this piece right here. So again, we'll find the inverse of A in H such that A times the inverse of A equals the identity. And again, this is going to satisfy our identity condition. And then once we get here, we're going to move on to show that the identity equals the inverse of A times A. And this will satisfy our closed under inverses condition. So let's actually start to work on this. We've identified A as x raised to 4, so A times the inverse of A equals x raised to 4 times the inverse of x raised to 4, which will give us x raised to 4 times the inverse of x raised to 4. Then we can combine our x's under one exponent, so that's x times the inverse of x raised to 4. And earlier we said that x times the inverse of x equals an identity, and so now we have the identity raised to 4. And of course, this just equals the identity. Now I'll go back the opposite direction, so this equals e raised to 4, and e raised to 4 can equal the inverse of x times x raised to 4. So we switch the position of the inverse. This then gives us the inverse of x raised to 4 times x raised to 4. We'll swap the positions of the exponents. So that's the inverse of x raised to 4 times x raised to 4. And if a equals x raised to 4, then we have the inverse of a times a. First, we see that the identity is indeed in H, so we've confirmed the existence of the identity. So we'll cross this off our list. Then we see that a times the inverse of a equals the identity, which equals the inverse of a times a, confirming H is indeed closed under inverses. So at this point, we've proved all 3 of our conditions, and I'll actually get rid of this stuff here as it's not a part of our formal proof. And there you have it. We've proven that the subset H is indeed a subgroup of G. If this video was helpful for you, give it a thumbs up, like the video, and subscribe to the channel for more math tutorials. I'm Coach T, and thanks for watching The Numbers Game.